Welcome to Crash Course Electronics, Halloween edition. Did you guys see that? The power's out. It's the week of Halloween, and all kinds of things are going wrong here inside of this lab. Power went out. We're on UPSs right now, powering everything up. That's why I'm in the dark. So I don't know. I've been hearing a lot of things. A lot of weird things are going on. So I don't know. Anyway, it's pretty scary. Now, what we're going to talk about is kind of scary also. H-bridges. And but we're going to try and make it not so scary. H-bridges are not half bridges, as opposed to half bridge and full bridge, which is kind of a bridge rectification for power. H-bridge is a motor driver, and it looks like an H, and that's where the name H-bridge comes from. So in this lecture, we're going to talk about how to build an H-bridge from the ground up. We're going to do it out of transistors, but you could do it out of MOSFETs, and typically that's what you would want to do is build it out of MOSFETs. You wouldn't want to use transistors because the transistors can't conduct enough power, and there's a number of other reasons. So, but it's easier to build it with transistors because a lot of people have those on hand, and we can kind of just grab a few parts and build something. Whereas working with FETs, a lot of times newer FETs are surface mount. You might have to solder them together and so forth. So anyway, we're just going to do this with transistors to get the kind of basic idea. So first thing let's do is let's go ahead and let's take a look. As a matter of fact, let's just Google for H-bridge here, and we'll say motor driver. All right, a lot of things come up here, and that's kind of what we're talking about. And these are obviously off-the-shelf drivers here. But let's go to images, and any of these are kind of what we're talking about. So let's grab something. Let's grab something. This is a FET-based one. This is that's a transistor-based one. There's kind of an abstract. Oh, this one's a good one. I like this one. All right, so let's go here and we'll say open image in new tab. All right, so what do we have here? So say you have a DC motor, all right? So a DC motor, and we're not talking about brushless motors. That's kind of a different thing. But a normal DC motor, you apply DC voltage to it. It rotates clockwise or counterclockwise. You reverse the polarity, then it rotates in the opposite direction. Standard DC motor. Now, a lot of times you want to be able to do that electronically. So you want to be able to make the motor go clockwise and then counterclockwise. So the problem is you've got this motor and you've got to basically apply plus and minus. And then to switch the direction, you've got to apply minus and plus. So how do you do that? Well, how you do it is with an H-bridge. And all an H-bridge is this kind of configuration. So each one of these is basically a switch, just a simple switch. And it could be a transistor or a FET, or it could be a switch even. All right, you could do this with switches if you wanted to make a simple circuit kind of for a classroom demo or something. All right, so let's take a look at it. So say in one case, we want current to flow down here, through here, and down here. All right, these are NPN transistors. So these transistors are going to turn on when we apply a high to them. All right, and they're going to turn off when we apply a low to them. All right. Now in this configuration, what the designer has done is he's tied this one, this input, to this input. All right, so we can turn these both on at the same time or both off, and then this B input he's tied over here to this input and tie that together. And that's kind of the two different ways that we want to turn this thing on. All right, so let's say that we apply a low to a B here. All right, so that means that Q2, all right, and Q3 are off. All right, now let's go and apply a high voltage to node A here. All right, so that means that Q1 and come around here, Q4 are both going to be on. So these are NPN transistors. We apply a high voltage to the base, right? We forward bias the transistor starts conducting, it turns on, it acts like a switch when it saturates, and this more or less becomes a short, right? Okay, same thing over here, Q4, this turns on, more or less becomes a short. So let's follow the current. So if we're up here, and say this was our positive supply, V sub Cc, maybe it's 12 volts or 9 volts, something like that, something to drive a motor with a lot of current. So current's going to flow down here. It can't get through Q3 because that's off, right? Q3 is off, right? So current's going to flow down here. Forget this diode for a minute. It's going to flow down through here. Now, can it get down through Q2? Nope, Q2 is off because remember B is turning Q2 off. So current's going to come down here. Now it can go through the motor, and it's going to want to come down here. Can't go through this diode, and then Q4 is on. So it's going to go through Q4, back down to ground. So basically, we've got this conduction path. So the motor is going to turn on, and it's going to rotate in one direction. Now, if we turn A off and we turn B on, apply a high voltage to that, we're going to have the opposite thing happen. So now we're going to turn Q2 on, and we're going to turn Q3 on. So we've got a plus voltage up here. Q1 is turned off. No current's going to flow there, but Q3 is turned on. So we're going to get current flowing through Q3, and Q4 is turned off. Nothing's going to happen there, so the current's going to have to go through the DC motor, come through here, and then it's going to flow through Q2 to ground, and boom, now the motor's going to rotate in the other direction. Now, the other cool thing that we can do is we can just turn these full blast on, right? Or we could apply a lower voltage, and that would cause less current to conduct inside of these branches. But that's a little bit hard to control because depending on the transistors or the FETs or this or that, what we really want to do is we really want to use these transistors or FETs in an on-off kind of switch fashion. So that means the best thing to do if we want to control how fast this motor rotates is use a PWM signal. Remember, a pulse width modulated signal, and put a pulse train on it, on-off, with a duty cycle, and then let that control it. So just turn it on, turn it off, turn it on, turn it off, and the duty cycle of that on and off would then change the rotation rate of the motor in either direction. All right, so this is kind of what an H-bridge is, and it looks like an H-bridge because here's kind of the H, and here's the vertical bar, and here's the other vertical bar. All right, so that's kind of what we're dealing with. All right, so now what we're going to do is we are going to do a number of things. We're going to design one of these. We're going to kind of draw it on paper real quick on the blackboard. Then we're going to create a simulation of it. So we're going to actually build this circuit up step by step inside of Proteus, Lab Center Proteus. And then we're going to go on the bench where I've already built one, and we're going to experiment with it so you can see it working. All right. So this is kind of what we're roughly going to make, very similar to what we're going to make actually. And then we're going to talk about what all these components are and why we're adding them, and some other features also. This is just a random, I just found this right now, and coincidentally it's similar to what we're going to actually build, but we're going to have some more features. Okay. All right. So let's go ahead and we will. And another thing also. Go ahead and if you search Wikipedia for H-bridge, now there's obviously countless references and white papers and explanations of H-bridges. Surprisingly, normally Wikipedia just has pages and pages of stuff, right? I'm really surprised. Wikipedia's H-bridge entry is pretty weak. There's probably a different way to spell it, maybe H-bridge or this or that. Something bigger will come up. But anyway, this is the very abstract, simplified version of the H-bridge. And there's our motor, and then there's just 4 switches. The switches can be anything. The problem is when you're building one of these H-bridges, you have these 4 switches, you have 4 different things you can turn on and off. So you could accidentally cause problems. What if you were to, so here's a power source, right? What if you were to turn on S1 and S2 simultaneously, leaving S3 and S4 off? Well, this would create a short right across the power supply. So whatever the internal impedance of S1 and S2 would be, you would get that kind of current flow. So you'd get the voltage divided by the impedance would give you the current. It could be a lot. It could actually burn these switches out. Same thing over here. You could short these two. You could turn S3 and turn S4 on and leave S1 and S2 off. And then in this case, you get another short here. All right. So you have to be careful shorting these, right? So this is why you'll see motor controllers or H-bridge controllers that are kind of intelligent, and they may have a command where you say, hey, turn the motor right, turn the motor left, and with an added PWM signal or some other analog signal, then it controls these switches so that you can't possibly short them together, because if you have individual control of them, then obviously you can short them together. Moreover, Uh, there's some things like, for example, say you're turning the motor clockwise, right? Let's just say, for example, if we have S1 and S4 closed, then the motor will sit and rotate clockwise. Now I want to change it and make it go counterclockwise. If we just immediately turn on S3 and S2, right? We open up S1 and S4 and then immediately hit S3 and S2. The motor's already has momentum. It's rotating in one direction. Then we're going to start rotating in another direction. So we're going to get kind of this inductive braking, and then it's going to start rotating the other direction. But there's going to be a huge surge of current, right? So these kinds of transitions, going from one direction to another direction, slowing down, speeding up, all that, some of these intelligent motor controllers are aware of how these motors react, and they can look at the back EMF of the motor, right? So they can better control the motor so that it's smoother making these transitions. So motor control, very complicated subject, but we're just going to take a first whack at it for something fun. One of the students in the course had mentioned he wanted to see a motor driver, and of course, I said I was going to do a motor driver, so here we are. So anyway, that's talking about the switches, and then here's the state space. So there's four possible switches. They can be on or off, right? So 2 to the 4th is 16. So here's your 16 combinations, and you can see here's all these short circuits, these braking states, coasting states, and then motor moves right, moves left, and all that. So kind of some interesting things that you can do, right? All right. And then just talks about some drivers and so forth, and then the use of N and P semiconductors or N-channel only semiconductors, why you might want to do that, and so forth. I'm not going to talk about that. I'll let you guys read all that. All right. Anyway, so let's go to our famous drawing program here. All right, here we go. And since it's Halloween time, let's do this in orange. All right, so let's start off with we'll come down here, and we're going to go across here. All right, and then we're going to draw our first transistor. And let's see, how do I want to draw these? How do I want to draw these? I want to draw, yes, let's draw in this direction here. All right. Okay, I'm going to try really hard to draw these nice, which is never easy with this drawing program. All right. And remember, NPN, the transistor, the emitter points away. Okay. And then here's kind of the center area where we're going to put the motor. There's the two bases. All right. So now what I'm going to do is I'm going to just kind of put a node here and a node here. Just kind of keep ourselves centered here. All right. Let's try and draw the transistor this way this time. Go like this. There's our collector. And remember, current always is flowing in the same direction, kind of downward, right? But then we either shift it to the left to right or right to left through the motor, right? And then that's what gives us the different direction changes of the motor here. All right, let's get our collector, get our emitters. Okay, and we got our bases. All right, that's looking good. Then let's maybe go down like this, and we'll go like this. And then down here is going to be ground. Okay. Then up here is going to be V sub CC. Let's make this one green at least. And let's just say, you know, for fun, this is, you know, 9 to 12 volts. A lot of times those are kind of your motor voltages, 6 to 12 volts, 9 to 12 volts. And this is a DC supply, obviously, and can supply a lot of current. All right, so we have our 4 different switches here. All right, so let's go ahead and label them. And I'm just going to label that Q1, Q2, Q3, Q4. All right. Now, let's get our motor in here. So let's go ahead and let's make our motor, let's make our motor red. So here's our motor. And motors kind of have this symbol like this sometimes. And now here's the interesting thing. We are just literally going to short it right to here. And we're going to short it right to here, just like that. All right, so those are wires, just shorted straight across. So there's our DC motor. All right, so we'll call that M1. All right, so now we've got 4 bases. We've got this thing potentially powered up. All right, now let's go ahead And let's add some, we'll do these in orange here. Let's do these, let's actually do these in blue. So let's go ahead and make sure this thing is always off. So when we're not doing anything to it, let's make sure it's off. So since these are NPN transistors, we're just going to put a resistor to ground on each one of the bases. And that just makes sure we're all safe. So when we're not doing anything, remember to turn an NPN transistor, we're going to apply a high voltage to the base, right? But when we're not doing anything, I don't want any funny business, so we're going to go like that, okay? Okay, so we have our 4 resistors, and now, what kind of transistors are these? Maybe let's say the transistors, for the transistors, maybe these are, 2N3904, or maybe 2N2222As, or there's a multitude. We basically just want NPN transistors, and then we might want transistors that can handle a half an amp or an amp. So you just kind of Google or DigiKey or Mauser or Octopart and search. But these little simple kind of low-cost ones will do, and these will be able to pass anywhere from 200 to 400 milliamperes. So you can, play around with them with a small DC motor. Okay, so just real simple little 5-10 cent transistors will get it done for these transistors. Okay, now so we've got these bases set up. All right, and then again, if you're watching this bonus video, that may mean that you've watched the whole class. You haven't watched the whole class, you're just skipping, and that's great. And that's what the idea of the bonus videos are. You can just kind of watch these out of order, and it doesn't really matter, and just kind of have fun. If you don't know how a transistor works, there's a lot of lectures on it. But in a nutshell, real quick here, let's pick a color. Pick this color maybe. So you got this transistor, and it's kind of like a switch in the way that we're going to use it. You can use it as an amplifier or a switch, and how this works is like this. If we apply a positive voltage right here, right, to an NPN transistor, then what we do is we start forward biasing or turning this transistor on, and then if there's a positive to negative voltage here, then what happens is we get a current flowing like this, and then a little bit of current flows here, and then adds up to this current. They both sum together, and we get a current like that. So basically, it's like a switch. So it's a current-controlled switch, all right, current-controlled switch. Okay. Now, let's see here. All right, so everything is off right now, and now we want to be able to turn everything on. Okay, so let's go ahead and let's add some more stuff here. So why don't we, so let's do this passively. So we're just going to use resistors. So let's add a resistor here, and a resistor here. And then what value should these things be? We'll talk about that. And that's why we simulate and we build things, so we can kind of tune and figure out what we want to do here. All right. So I'm going to tell you right now, let's go ahead and make these pull downs. We could make them anywhere from 10K to 100K. We want to just make sure the transistors are not on, so they're kind of being held off. So we'll just call these 100K, 100K ohm. All right. And again, you got to play with these values. You got to see how the whole system works together and what kind of currents are being generated and so forth. All right, so those are 100K to ground, and that's going to kind of keep those things off. Now, we really want to turn these transistors on really hard, right? These are like switches. We want to use these transistors as switches. So we're going to turn these things on really hard. So for these resistors here, I want to go ahead and let's make these like 100 ohm to 220 ohms, so real small. All right, and so let's go. We'll call them 220s for now. 220 ohm, 220 ohm. All right, well, we're going to play with this, right? 220 ohm and 220 ohm. For example, again, if you don't know transistors, you'll kind of get lost a little bit here, but so if this is 220 ohm, and then let's go ahead and let's put some switches on the other end of these things. So we're going to put a switch here, we're going to put a switch here, we're going to put a switch here, a switch here that looks like this. So why don't we put a little momentary switch like that, and then the other end of this is going to go up to this V sub CC. So I'm just going to, again, just put V sub CC, the same voltage it's going to be. Whatever this is going to be the same. All right. So let's put another switch here, momentary switch to V sub CC, and momentary switch here. And this is kind of the symbol for a little push button momentary switch. All right, and right here. All right. So I got this kind of architecture. So that looks good. So you have these 4 switches. Let's name these a little bit. All right, let's name these switches. So this Q1, so we'll just call this S1, we'll call this S3, we'll call this S4, and we'll call this S2. The resistors, I don't care so much about naming them. All right, so as we close these, so if we were to close S1 and S4, we would turn the motor on and it would go in one direction. All right, now let's go back and talk about this a little bit. So this node right here, is equal to 0 volts. So this is equal to 0 volts right here. All right, now when this transistor is on, and it's on really, really hard, right? If you guys recall, for those that have done this, this voltage drop from the base to the emitter is going to be approximately 0.6 to 0.7 volts. 0.6 to 0.7 volts. All right, so that's 0.7 volts. So if this is at V sub CC, then the total voltage drop over this 220 ohm is going to be V sub CC minus 0.7, right? That would be the voltage drop. So if we wanted to find the current here, so if we want to find the current through here, let's use green. So we want to find the current through here. That's going to kind of come through here. And this current right here is called I sub B. I sub B going into the base, right? So I sub B, roughly, is equal to what? V sub CC minus this 0.7 volts over this 220 ohms, right? And if we plug in real numbers, let's just say that we're using 12 volts here. So we plug in 12 volts minus 0.7 volts over 220 ohms, right? Is going to give us 11.3 volts, 11.3 volts over 220 ohms. All right, let's get our calculator out and pray that we have enough photons to do this. All right, so we've got about 51 milliamperes. 51 milliamperes. So that's a lot of current, right? So we're really driving this thing really hard. We don't need that much current to turn it on, but we're just going to leave it at that. We can always make these resistors a little bit bigger. Okay, so the point is that when we close these switches, so let's do some closures. So if we say S1 plus S4, and by plus that means these are all the switches that are closed, right? So in this state, S1 plus S4, what's going to happen? Well, in that case, we're going to get a current, and again, I'm going to use green here. So we're going to close S1 and we're going to close S4, all right? So when we do that, what's going to happen is we're going to get this V sub CC here, right, giving us that base current. That's going to turn on that transistor. We're going to get this V sub CC here. We're going to turn on this transistor, right? And when we turn these transistors on, we're going to get a big current over here in the collector side, right? So we're going to get current that's going to flow down here, right? And it's going to go down here. And the little base current's going to add up with it, but we don't care about that right now. Then it's going to go here. It's going to go this direction. It's going to go right through the motor, turning the motor on. It's going to go down here. Again, it's going to go through here. It's going to sum up with this little base current here. And then it's going to go to ground. So that's what's going to happen when we turn on S1 and S4. All right, cool. So now let's back up and let's try another one. So now what happens if we do the other state, which is, say, let's turn on S3 and S2. So state S3 plus S2. What goes on in that situation, right? So let's go ahead and we'll pick a different color here. So S2, where's S2? S3 and S2, S2 and S3, these two right here. All right, so if we close this, we're basically going to get a current here. We're going to get a base current, right? That base current's going to turn on this transistor, and then it's going to end up going down here. Small base current, like 50 milliamperes. All right, then we're going to turn this transistor on also. We've already got that little line there, but just bear with me. and we're going to turn that on. So both transistors are going to be turned on, and both of those base currents are going to shoot out of those emitters, right? But we're going to turn these transistors on. So each one of these transistors is going to basically act like a closed switch. So now current's going to come from the source. It's going to come down this way. It's going to go through here. This time it's going to flow in this direction. Of course, the little base current here adds up into it. It's going to go through our motor here, down here. All right, keep going, keep going, keep going. We're going to pick up that base current right there, and we're going to go down to ground. And so that's the other state right there. So those are our two different motor states. Turning on 100% full is much power as this circuit can flow, as much current as the circuit can flow. The motors are going to turn on and then rotate. Now, how can we control this? Well, we could control how much we turn these bases on. We could control them with analog, but the problem is these are open loop circuits, right? And we've talked about this before. Each one of these transistors, if we just use it in this kind of switch configuration right here, depending on what the gain is of the transistor, could be 100, 200, 300, 400, you're going to get kind of a different amount of current flow. So we need feedback. We need to make an actual amplifier and have feedback so we have some control over it, so that whatever the gain is, the transistor gain is factored out, so we get a gain set by components, right? That's what we really want, so we could control the gain, right? But at this simple configuration, we can't do that. So what else can we do? Well, what we can do is, instead of having little mechanical switches here for our example, what we can do is we can use PWM, right? And if you don't know what this is, pulse width modulation. And the whole idea of this is, right, and of course in the course, we talk about this, and we have a waveform here. And let's say that we've got a signal, let's say a kilohertz, 1 kilohertz, right? So we got, say, a 1 kilohertz signal. All right. So that means the period of each one of the waveforms of each one of the individual cycles is going to be 1 millisecond. 1 millisecond. All right. So that means from here, so say here's one of these waveforms, goes from here down to here. That would be one complete cycle right here. This is the high part, and this is the low part. From here to here is 1 millisecond. Okay, 1 millisecond. All right, that's one cycle. Then we have another cycle, goes up, goes down, and so forth. Now, this right here, if we look at this, here is when the waveform is high, and here is when the waveform is low. You can see they're equal, right? So it's 50-50 right now. The ratio of this, so as we change the ratio of the high to the low, so coming back here, we can start to make a waveform that looks like this. It can be long, 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 and then it can be off just a little bit, and then long, 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 and then off just a little bit, and on, and so forth, right? Or we could flip it around, and we could just turn it on just a little bit, and then it's off, 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 turn it on a little bit, and then it's off, 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 off. And the total cycle time is always the same. It's that 1 millisecond, but how long it's on or off, right? That's the modulation. So the pulse width modulation, we're modulating the width, how long this thing is on or off. So in essence, if we were to take these signals and then apply them to these switches, right? All right, and of course we'd have to apply them to the correct switches. So this switch and this switch, or this switch and this switch. We can turn these motors on just a little bit of time. All right, and so they're going to turn on just a little bit of time, and what that is going to result in is the energy transfer. Instead of being full blast on, it's going to be a percentage of full power, so the motor is going to rotate at a lower angular velocity. And that's kind of how you can control the motor's rotation rate digitally with a pulse width modulation. All right, so that is an H-bridge, and then of course we could just switch these. Right, we could switch these guys, for FETs, okay? And that's what you would do. So these are NPN transistors, all right? And then NPNs are recommended for, there's a number of reasons, but Typically, if you're going to do it with transistors, you'll use NPNs. But if you do it with FETs, then a lot of times what you'll see is on the high side here, you'll see a P-type FET, a P-type FET, then you'll see an N-type FET and an N-type FET. Because of the charge carriers, you want to put the P-types on the high side, the N-types on the low side, but then they turn on and off with different voltages, right? So that you kind of have to play around with these inputs a little bit more. But the reason why you like FETs is the on resistance is very low. You're talking about milliohms, right? So these things are nearly dead shorts. So you can create these H-bridges that can flow enormous amounts of current for very cheap, right? So you might be able to make a 10, 20, 50 amp H-bridge with very cheap parts as opposed to doing with transistors, which would be much more expensive. Okay, all right, so that's kind of what we're building, all right? And one other thing I want to talk about here, I want to add. We are driving motors here, all right? And one thing that we learned when we were doing our course lectures is when we're driving motors is that when this motor is, we're driving the motor, and then when we turn the motor off, this is an inductor inside of here, and this inductor is going to want to maintain this current. And so what happens is the inductor creates a voltage, right, and in the opposite direction. It can damage the transistors, all right? So what we do is we're going to put these catch diodes here, and we're going to put them in this configuration right here. So just like this, over each one, we're going to put a diode. And this is for the, the inductive kick. We've used a few different names to kind of identify these, but they're going to go in this configuration right here. Sorry if it's a little bit hard to see through things, but it's hard for me to erase this. So they're going to go, so normal current is going to flow down in this direction right here, all right? And when that happens, and let's use a different color for that. Let's use so many colors, this one. All right, so let's say that we got the motor and the motor is running like this, right? And let's do that a little bit better. The motor's running like this, like this, like this, like this, like this, and down like that, right? When we turn this motor off, what's going to happen is we're going to get a large positive voltage here, and it's going to want to drive current this direction, and instead of the current going back up here through this transistor, it's going to go through this diode. And then you can kind of follow that same pattern, and it'll work always the same. So the diodes always go in the same direction, the opposite of the normal current flow of the transistors or of the FETs. And then that will protect these semiconductor devices, and they won't get blown up, which can actually happen quite easily. All right, and the other thing is what kind of diodes. So when you guys do this, you can use a 1N4001, a simple little diode, or you can use a Schottky diode, which has a much lower on voltage. But 1N4001, 2, 3, 4, 5, 6, any of those will be fine. Just run of the mill when you're just building a fun circuit. If you're going to do real motor control, please do not build your own H-bridges. Companies spend years literally engineering these things and optimizing these things and doing a very deep analysis of them, testing them out with different motors and all that for all those different conditions I talked about, and thermal this, and being able to control the motor, break the motor, and so many different things, but this is just for fun so you can kind of see the process. Okay, now let's go to our simulation tool. Where is it? Where'd it go? Here it is here. Okay, now. Okay, so the first thing, you know what, let's move this and move it right here. Okay, and we are always out of time. I do these big lectures. I do them unscripted, so they're honest, and we kind of talk about things as we go. And we just don't have a lot of time, especially with the bonus lecture, because I want it to be one lecture and not 2 or 3 or 4. So we can only do so much stuff. Now, if you haven't seen Proteus, this is Lab Center Proteus. If you go to labcenter.com, this is a simulation, PCB layout, schematic design. This is an awesome tool. Like Circuit Maker, it's very cool. Like Circuit Studio, it's very cool. Except what this has is simulation, where a circuit maker the PCB tool we're going to use in the course for free does not have simulation. So this is not free, but you can use the simulator for free, but you just can't save. All right. So if again you're coming to this for the first time, you're like, what's this? This is Lab Center Proteus. Go to labcenter.com, download it's totally free, install it, and then you can build these things. You can just kind of copy this, and but you can load simulations. So this is a simulation HBridge 01. It'll be inside of the lecture materials for this lecture. So just look in the download section and just download the zip file. Boom, it'll be in there. All right. Okay. What are we doing? All right, so let's take a look at this. So this is basically what I just designed right here, right? This is that. Okay, let's take a look. All right, so we've got our motor here, which is just a standard motor device from Proteus. And we've got our transistors. And this is just some random transistors, ZTX 450. That I looked up as one of the parts here that this tool had. Remember, if we want to run the simulator, we need models of things, and if we don't have a model, then a lot of times we'll just use a transistor that, or a FET, or a device that's similar to it, and then we build our real devices on solderless breadboard or printed circuit boards. Then we kind of have to extrapolate or imagine with the real parts it's going to work a little bit different, but we can kind of use models that are similar, right? Because we can't build all these models in here. Now with some tools you can give models for the devices, full complex models, but this company gives you these models and there's not much you can do. You can't create your own models, but a lot of times they're parameterized so you can actually mess with them a little bit. For example, if we go to the motor, it says how many revolutions. I believe this is revolutions per minute. And then the load resistance. What's the motor's DC resistance? 5 ohms. But there's not a whole lot of other properties here. Nominal voltage, 12 volts. You know, so there's not much else here you can mess with, right? If we go to the transistors, all right, again, not much else we can mess with, right? So again, depending on what, you know, and here's these Schottky diodes. Again, the model is kind of intrinsic, so we can't mess with it. But sometimes you can mess with the models more if they expose some of the parameters. All right, so let's look at the circuit. So what do we have here? We have a voltage source, a DC source, this motor 12. So motor 12, and it's 12 volts. It's DC. Okay, cool. Down here we've got ground. All right, so we've got each one of our legs of our H-bridge. So we've got, again, these are NPN transistors. The emitter is pointing out, it's NPN, 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 NPN. Then we've got these Schottky diodes. Instead of using the 1N4001, we're just using Schottkys. In this case, these are pretty high current Schottkys, I believe, if we were to look them up, if we were to take that number, right? And if we were to go over here to our favorite little tool, DigiKey, and we were to look these up. Well, let's see, what's the story with these? 38 cents, they can handle 30 volts and an amp of rectified current. Good enough, good enough. And their forward voltage is 560 millivolts at 1 amp. So that's pretty good. It's better than the 1N4001, which is going to be about 0.7, maybe even 0.8 volts. It'll drop. And remember, ideally, we want it to drop 0. We want it to be perfect. So we just want it to be a diode, but not drop any voltage, right? All right. Anyway, moving back. So here's our configuration, and then we've got our switches, 1, 2, 3, 4. These are interactive switches, so we can kind of turn them on and turn them off. All right, and these are not momentary because there's no way to press two things at once. So we turn them on and turn them off, so they're latching. All right, and let's see. Okay, now we also see there's some capacitors here. I want to talk about these. Whenever you're doing motor control, a lot of times the motors generate a lot of noise, electrical noise. So what you'll do is on the plus side and the minus side, and this motor here, there's no plus or minus, right? It goes either way, so there's no, you know, correct way to connect it. We can just arbitrarily say one side is plus, one is minus. In any case, some of the design tactics that you'll see designers do when they're putting motors in things is they'll put a small capacitor on the plus and minus to ground, and that gets rid of one kind of noise. And that capacitor typically is like 0.01 to a 0.1 microfarad, in that kind of range. And then you'll put one right across the capacitor, the motor leads. You'll put a capacitor across that, and that might be a little bit smaller, 0.01 to 0.001 microfarads. All right. Then another thing you might even see is putting inductors, extra inductors to get rid of high frequency noise inside of the power lines as well. All right, but we don't have this. So we just have a few capacitors here for noise. All right, Then we have our resistors here looking back at our design. You know, we've got our base resistors, right, 220 ohm, and then we've got our base pull-down resistors to keep the thing off, to keep each transistor off. And again, we used 100K, 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 and then these are 220, 220, 220, 220 for the base resistors that are going to be the injection path for the base. All right. And then you see I've got a bunch of instrumentation here for you, so you can kind of see what's going on, right? And then what's interesting is, will this match the circuit that we build on the bench, which we'll do in a little while. Okay, then up here, you see I've got a big capacitor, this big bulk capacitor. When we turn these motors on, right, there's going to be a lot of inrush current, a lot of currents, and we don't want to pull that from the power supply. So even though this is a simulation, we still want to have good design, and so you want to put big capacitance on these motors, 220, 470, 1,000 microfarads or more, all right? And that way, when you need that current, it'll pull from this capacitor and not from the power supply and dip down your power supply and potentially cause ripples and issues with your other power supplies that are pulling maybe from this 12 volt to get your digital supplies, right? Okay, we're always concerned about that. Okay, so I think, let me see if we can get this on the screen. So what I'm going to do is I'm going to kind of put it just like that. Proteus is this lab center. Lab Center Proteus is a United Kingdom company, and you know, here was the interesting thing. When they made this tool, they were kind of pushing the limits of Windows when they made this tool initially, and they kind of came up with their own things. And then Windows got really, really, really good. And now this tool, if you look at it, looks very dated. It looks like a 90s tool, right? And a lot of things are very 90s-ish. They're not like normal Windows or what you would expect on a Macintosh either. So, you know, you scroll the scrub wheel to kind of make things, you can't do this smoothly. There's just lots of issues that make navigation a little bit different than what you would expect just with any Windows app. So it's kind of like hard to get things centered and all that. Anyway, here we go. All right, so I'm going to run the simulation. And I've got 9 messages. I got 2 messages. Okay, we look good. So here's the 2 messages. Everything's working. Simulation log, cool. And it's animating, and CPU load is 0%, which is completely incorrect, I'm sure. All right, so it's running, and we can see all these voltages and everything is going here. Now, the motor is just sitting there. All right, so now if we turn this switch on, right, nothing happens, right? If we turn this switch on, nothing happens. This switch, nothing happens. We got to turn 2 of these things on, right? All right, so let's go ahead and let's turn this transistor on and this transistor, and we'll get a current flowing through this guy like this. Here we go. So I turn this one on. Now look what's going on here. Right now in the collector circuit, we have a very little current because we haven't turned the emitter here has no ground right now. It's still floating because this is not turned on. All right, but now we're going to go ahead and turn this one on. Boom. And now in the video, you can't really see which way this is turning. As a matter of fact, let's go ahead. Let's modify that. Let's see if we can make that a little bit more. Instead of 10,000, let's make it just 5. Oops, 5. Maybe we'll be able to see it a little bit better. All right, and I'm going to save that. So here we go. We're going to run it. Okay, and now this is on and this is on. So now we can actually see it turning the correct way, and it's not doing any kind of crazy superimposing on our eyes. So it's turning counterclockwise right now, or excuse me, clockwise. Yes, it's late. I'm tired. I always do these really late, so it's real quiet when I'm recording. All right. So it's turning clockwise right now. Now let's take a look at some of these currents. So coming through this node right here, we have 483 microamperes, which is getting dragged through here. And then over here we have 546. So whoa, wait, what's going on? How can we be pulling only 483, but then we've got 546? Well, remember, we've got 43 right here. Then we have some base current. How much do we have here? 22 milliamperes. We're pushing through this base. That's going to add, right? So whatever this current is here, we're going to add to it. Then we've got that current coming through here, coming through here, coming through here, coming through here. Then here we go. Then what are we going to add to it again? We're going to add this current here, this 41 milliamperes, which is driving this base here. And so that 41 is going to add, when you add all those together, you get 546 milliamperes. Boom, going down to ground. All right, so this is working exactly as we would expect. Let's turn this off. All right, and now on these little switches, you got to hit them just right. And let's go in the other direction. Boom and boom. And now we're going in the other direction. We're going counterclockwise. We're going backwards in time. Cool. So that's working. And again, we have almost a very symmetrical configuration. We have 483 on this leg now, and over here we have 546, the opposite way. So current is flowing down, down, down through Q12. And these numbers, because I did a lot of copy and pasting, these numbers are kind of crazy. Q12, then it comes through here, then it comes through M1, and then it goes through Q14, and then back down to ground. Okay, now let's have some fun because we can't blow this up. Let's short this thing out. So I'm going to short these two switches. So right now I'm getting no current through here, right? I'm only getting this base current here, just this right here, right? We're just getting this, but we're not getting a lot of collector current. So watch this, boom. Now we're getting currents coming from the source, 574 milliamperes are coming through here. Then we're getting our 70 milliamperes here, ouch, and that's adding up. And then we're getting our base current here, which it's splitting off in both directions here, and then they all sum up, and we get 644 milliamperes. The good thing about transistors is the impedance of the transistor itself, right? It's not going to flow, much more current than it can handle. It's going to kind of get stuck and kind of not be able to blow itself out. Now, if you keep running it, yeah, it's going to pop, it's going to overheat. But the nice thing is it's not going to instantaneously just explode. All right, so the simulation, we can't hurt that. Now, what happens if we turn them both on? Let's check. We turn this on now, and then we turn this on. So what's interesting here is we're shorting this side out, but what's happening is we're kind of creating this asymmetrical voltage situation so that we can get some rotation, some current flowing through the motor because it's an unbalanced circuit. All right, now let's rebalance it, and then let's unbalance it over here. All right, and unbalance it over here. See? So you can do that. That would be very bad. You don't want to do that, right? So you want to keep all these back open. Okay. And that one. There we go. So there is our H-bridge. And again, what you want to do now is these four things, since you want to make sure you don't ever turn this motor on and short things out, you would tie like switch 9 and switch 11 to one signal, then switch 10 and switch 8 to one signal, and then you would only turn one on or the other one on. And then even better yet, you would make sure that they're inversions of each other, so you can only turn, when you turn one on, the other one turns off, or when you turn one off, the other one turns on. That way you never ever hurt your motor. All right. Or your drivers, your transistors, or your FETs. Okay, so we are running out of time. Let's get over to the bench and let's go ahead and play with that. So I'll see you over there. Okay, so what do we have here is we've got a model of our H-bridge, almost identical to what we built. We've got our 4 switches, we've got our 4 transistors, we've got our motor plugged in right here, which is suspended on this device here. It's a little, so the focus is, we're focusing here, so we can't really see this. But anyway, the motor's over there. We'll get to that in a minute. All right, then we've got a little bit of instrumentation. Right here, I'm measuring current, and we're going to see that on a meter, which we'll bring in. All right, so we can see that once we back away from this. Everything is identical. We've got our capacitors there that we saw. We've got our diodes. We've got our kickback diodes on there. And now another interesting thing that we have is over here, down here. For one of the switches, I have a PWM signal from my signal generator that I can turn on and enable. So that signal's at 50 kilohertz, and unfortunately, the signal only goes up to 10 volts. All right, whereas we're powering this with a 12-volt supply. So those bases, so when we turn this base on, we can't turn it on super hard as we can with the switches, but hard enough. But we're not going to use that at first. All right, so what we're going to do is I'm going to back away here a little bit so we can get most of the stuff in here so we can kind of see. All right, so let's put this in here. All right, and this is, again, this is always very hard to film all this stuff and get everything on here so you can kind of see everything. Obviously, we don't have a film crew. All right, and I'm going to, how about I put this right here maybe? Okay, so here's the deal. Let's see if everything's on. So the power supply is on. The signal generator is off. So the signal that we're injecting into this one switch is off right now. So the switch will turn it on. All right, and then keep an eye on this current right here. So this is the amount of current that's going to be flowing. So if we want to turn the motor in one direction, we basically need to turn on two of these switches. So let's try these two right here. Let me get my hand out of the way. All right, so I'll press one and then press the other. And you can see we're doing about 300, 250, let it stabilize, about 247. Now, here's the interesting thing. All right, so first, what direction is that turning? All right, all right, so that's turning, yeah, so that's turning counterclockwise. Now watch that current. So see how the current is high? Because the motor, we're spinning the motor up and then it drops down. So there's two kinds of things happening here. Right when I turn this motor on, boom, boom, look at that, 0.4 amps, roughly 0.4. Then it drops down. So that's the initial start current. That's the start current, right? Then there's what's called stall current. And let me do this with my fingers here. I'm going to turn these both on. And I'm going to stop this motor. All right? And look at that, 0.4, and I'll let it go. So we got to be able to handle that stall current, okay, without blowing things up. All right, so then it's going that direction. All right, so now I'm going to, the current's going to be roughly the same, so I'm going to kind of cover this. You'll see my fingers cover this a little bit here. It's kind of hard to get in here. Let me see. All right, so I'm going to do these two switches here and do it the other way. Here we go. All right, I'll kind of put my fingers there, and then you can see it's going clockwise. Now look at the current. The current's the same. It starts off high, and then it drops back down to the same. Now, let's try a different experiment. So now, if I let go of these, let's look how long it takes to coast down. Ready? 1, 2, 3, 4, 5. The switches are actually burning my fingers. These switches are not rated for this current. They're actually burning my fingers. Let's do that again. Rev it all the way up. And it's burning my fingers. 1, 2, 3, 4, 5. Ouch. Ah. Okay, so that switch is getting really hot. Here we go. We're going to do it again, but this time I'm going to stop it with the other two switches. So I'm going to reverse the direction. So forget the current. You're not going to watch that. Okay, so here we go. We're going to go in one direction. When we hear the motor, full blast. And then, do you see what I did? I used the other direction as a brake and then switched it really fast. So, boom. All right, so that's braking. Okay. Okay, so there is the H-bridge. The H-bridge works, and then we can change directions very quickly. Instead of letting it coast down, we can just flip directions, and of course that's going to cause more current draw. All right. Now, over here, we've got my, let me see if I can point my finger. Over here someplace, there's a signal generator, and that signal generator right now is at a 20% duty cycle. All right, so what I'm going to do is I'm going to turn the signal generator on. It's going to basically pulse this for us with a 20% duty cycle. And we're going to hold this one and just keep this one on. Okay, so what I'm going to do is I'm going to put my finger around here and I'm going to turn on the signal generator. Signal generator is on. Everyone's happy. I'm going to turn this one on and then notice it starts turning. But notice what the current is. It's less. See? Because we're PWMing it. All right. All right. Isn't that cool? Now, I'm going to turn it on, and now I'm going to adjust the duty cycle manually over here. So first, let's turn it up. And see, didn't pull that 0.4 amps, and it's not hanging at almost 300 milliamps. It's only hanging at 200 milliamps, right? Okay, now, here we go. It's at 20% duty cycle. Here comes 30. Look at that. Here comes 40, 50, 60, 70, 80, and with this tool I can only go 20% to 80%. You can't go less than 20 and greater than 80. But look at it, isn't that cool? And then now watch it slow it down. Isn't that cool? All right, that is PWMing that one leg, right? And of course you could PWM both, you could overlap the PWMs, you do whatever you want, you can do all kinds of cool things. Okay, so that is the H-bridge. All right, so we've made a discrete H-bridge out of transistors, very cheap, it does work. This is not a tiny motor. Let me show this to you. This is a pretty big motor. I think this particular motor, you could probably put an amp through it. Big motor, We're just using a little simple transistor. Stuff is definitely getting hot, but this is a good starting design to kind of get things going. And then you can kind of work from here. And then you could change these to FETs. You could control things with only one control signal. You could get rid of these switches and then connect these directly to a microcontroller so you could turn it on and so forth. And that's exactly what a HBridge chip does, right? So let me see here. So I have, let's move these out of the way just a little bit here. Move this out of the way for you. And then I've got a couple manufacturers here. So here are some HBridges right here, and that I bought just to check them out. One's really, really tiny and one's a little bit larger. So let's go ahead and let's take a look at these real quick on the computer. There's thousands of HBridges and then motor controllers and so forth. So there's no limit to what you can do as far as cost and performance. But these are just a couple cheap ones and simpler ones to solder together. So let's take a quick look at the computer and take a look at these. All right, let's go back to the computer. Okay, so we're back here on the computer and we're taking a look at the first little motor driver. So this is this SIP 2100, and if we click on this, we look and we see at 1,000 it's about $1. And what I like about this is it'll go up to an amp, and it's pretty simple. And let's go ahead and let's grab the data sheet. And you can see it right here. So it's a very simple 8-pin package, and I believe it only is an SOIC package. I don't think there's a through-hole version of it. Yeah, it's only an SOIC 8. And very simple though. It's got power here, so there's your power, right? And then it's got ground, and then it's just got a few control signals. So here's NA, NB, out A, out B to your motor. So right here, here's out A and out B. This is a horrible PDF. This goes to your motor right here, all right? And then these S signals here, SA and SB, I believe these are for sensing. These might be sensing signals. And then, yeah, and then these ends, NA and NB, this is what controls the motor. So you only have 4 different combinations because they're tied together, so you can't really get in too much trouble. So 1, 0 turns the motor in one direction, on and off. 0, 1 turns the motor in the other direction. 0, 0 turns the motor completely off, both outputs. And then 1, 1 is interesting. That puts them into high Z. All right, so instead of grounding both outputs, it puts it into high Z. All right, and then these S signals, this SA and SB, are for feedback. So if we look through here, and this is a brand new product. Let me see, here it is right here. Driver output return A, driver output return B, so you can kind of see what's going on with those signals. So this is a nice little part, very simple and very easy to use. So I like this right here, and this will drive a pretty big motor. If you want to do something kind of, you know, this isn't, you're not doing a discrete design now, right? But you're doing one that you're using an IC that doesn't have a whole lot of control logic, but it does have some control logic, right? It doesn't have a lot of super advanced features, but it does have some. Okay, so that's that one. Now let's take a look at the other one. Let's search for that. All right, and the other one is, all right, so the other one is this MP6513GJ-Z. And what I like about this is it's teeny tiny. It's one of these SOT 2.3 kind of packages, right? So this is really cool. And this one's a little less current. This one's 800 milliamperes, but it works at a wider voltage range, which is kind of cool. And let's take a look at that. Very cheap, you know, again, under $1. So look how simple this one is. So you just put your motor there, your DC motor, or you could put a stepper motor too. All right, and then we've got power here, we've got ground here, and this one's only got 2 signals, so you don't have those feedback signals this time. You got in1 and in2, and then there should be a little truth table again. But this is a great way to control a motor and be safe with a nice FET driver, right? And let's see if there's a little truth table, and let's see, and then look at that, see those are pulled down, so there's no funny business on those inputs, right? And these are using FETs again, right? Like what you should use. And there's our truth table. There we go, right there. So there's a truth table kind of showing what's going on. If they're both low, it's in coast mode. Low, high, reverse. High, low, it's in forward. And then high, high, brake. So high, high, no matter which way it's turning, it will want to stop it, all right? Which is very cool. All right, so this has braking also, which is nice. So again, that's this part right here. And you know what I'll do is in the materials for this lecture, I'll throw the data sheets for both of these chips inside of that zip file, so you have the data sheets. The data sheets are public domain, you can get them, but just so you don't have to remember this number. But like I said, there's thousands of motor drivers and HBridges, so kind of look around, see what you want, see what would help you out with whatever it is that you're doing. All right, so that is it. So, you know, that's kind of where we started from. All right, we kind of designed through this. We talked about it, how it works and so forth. We went and built our simulation. The simulation file will be inside of the lecture materials in the zip simulation, HBridge 01, 02, whatever I end up saving it as. So as a matter of fact, save right now, and I think, yeah, we'll just leave it like that. So that'll be inside of there. We did the bench work so you could see it actually work, and it does actually work. And that is motor control. So very cool. Now, these are brushed DC motors, and you're going to have to look up what that means, but there's brushes inside of it, and there's commutation that goes on, and then there's a permanent magnet, and there's a electromagnet, and it's a super ingenious. I mean, electric motors are fascinating. There's some really good YouTube videos. I didn't take time to find them for you, but there's, you know, just a little segue here. Depending how old you are, if you're my age, about half a century old, back in the 50s, 40s, 50s, 60s, mostly I think the 40s or 50s, there were these educational videos. The world used to be a different place, especially in the United States. In the United States, like if you bought a radio, you got the schematics to the radio. It explained how it worked. People wanted to know how things work. Now they just could care less, right? Which is really sad. But there were these videos that they made which would show how things worked, and there were a whole series of them. And I think it maybe was for military so that people could understand. But like people wanted to know how a car worked. How does a differential, the rear end work, or brakes work, or this? And they had some motor videos that have amazing animation made in the 50s. And if you YouTube around and say, the operation of a DC motor, how does a DC motor work or whatever, you might even stumble upon it. And they're actually pretty amazing. I mean, these things are over half a century old, and it's showing electromagnetic induction, it's showing motors, it's just very amazing to me that we had this technology, you know, 70 years ago, more, right? 100 years. TV was invented in 1898, roughly. First cathode ray tubes, right? Crazy, huh? Over 100 years ago. But anyway, we had this stuff. And so those videos show this, and they show it in a really clear way, where some of the more modern stuff is kind of it's you know, it's hard to see what's going on. But anyway, you can look and see how these motors work for these brushed motors. And then there's these brushless motors where we get rid of this mechanical aspect and we control it completely electronically. You need a different kind of control system for that, all right? Because the motors themselves need to be sensed, usually with a magnetic sensor, a Hall sensor, has to sense what's going on magnetically in the motor, and then use that information to control the motor. But with standard, simple, brushed DC motors, these are the kind of controllers that you need. All right, so that's it for this lecture. I hope you liked it, and that's it. So good bonus lecture, and we'll see what we do next time. All right, so I'll see you in the next one. Bye.